Welcome, guys. This is going to be AP Stats, Module 2, Lesson 7, Geometric Random Variables. This is going to be covered in 4.12 in AP Classroom and Section 6.3 in your textbook. So we have a scenario. Let's read through it. Suppose your teacher is planning on to give you 10 problems for homework. As an alternative, you can agree to play the Lucky Day game. Here's how it works. A student will be selected at random from your class and be asked to pick a day of the week. So, for example, Thursday. Now, your teacher is going to use technology to randomly choose a day of the week. So we have random, so we don't have to worry about the independence rule. If the student picks the correct day, the class will have only one homework problem. Yay. If the student picks the wrong day, your teacher will select another student from the class at random. The chosen student will pick a day of the week, and your teacher will use technology to choose a lucky day. If the student gets it right, your class will have two homework problems. The game continues until a student correctly picks the lucky day. Your teacher will assign a number of homework problems that is equal to the total number of picks made by the members of your class. Does that seem fair to you? Well, the problem here is that this is not a set number of trials. So we're not guaranteed how many homework problems we're going to end up with. So this is not a binomial. We do have the right or wrong, so it's binary. It's independent since things were randomly selected. And our probability of getting the correct day is going to be 1 out of 7 because there are 7 days in a week. So this is not a binomial, but because we're going to stop when we get it correctly, we call this a geometric random variable. So let's follow through with this first part. We want to know the probability that the class receives exactly 10 homework problems as a result of playing the Lucky Day game. So the way you set up a geometric random variable is you think about like we have the wrong answer first, okay? So we want to know what's it going to be like on the 10th try. So it means we want to get it right on the 10th try. So it's going to be wrong 9 times. So the probability of getting it wrong is going to be 6 out of 7. And then we just multiply, by itself 9 times, or you can raise it to the ninth power. And then we're going to end with the correct one. So that's going to be 1 out of 7 at the end. So that's going to be 6 out of 7 to the ninth power, and then times 1 out of 7 at the end. So what does that look like? Well, let's have a little more cleaned out version of this for you. So we got 9 wrongs, 1 right. 6 out of 7 to the 9 times 1 out of 7 is going to be about 0.03567. So you have a 3.567 chance of getting it right on the 10th try and therefore getting 10 homework questions. And there's our math to back it up. So use your calculator to get that decimal. And let's look at another scenario. Find the probability that x is less than 10. Describe it in words. Well, we could do what we did before. Now, less than 10 means 9, 8, 7, 6, 5, all the way down to 1. So we can get it right the first time, second time, third time, fourth time, fifth time, and so on. And that's a lot of math, but it's doable. Use your calculator and you can add those together very carefully. Now, we do have a calculator workaround for this one. So first, let me show you what the geometric, if you go to second vars, right under binomial, and you'll see the binomial, then you keep going down all the way to the end, you'll see the PDF and CDF. So let me show you PDF first. In the previous problem we did it getting on the 10th try exactly, and there's your 3.56%. Now, if I want to do the less than 10th, what I want to do is go to CDF, that means cumulative, and we're still going to use 1 out of 7. That's our probability of success. In this case, you want to do 9 because it's gonna count there and all the way down to 1. And that's going to give you about 75%. So in words, that probability would be something like um, the class would have a 75% chance of having 9 or less homework problems for over many, many random selections. So let's take a look at what that looks like. Again, go to your second vars, go to geometric CDF, and you can get all your values from your calculator, but you do want to write this. So if you're going to use geometric CDF, make sure that you put this down And make sure your inputs say less than or equal to 9 and don't just say x equals 9 because we're doing a combined number. So in terms of the description, the probability the class receives less than 10 homework problems is 0.7503, or you could say the probability the class receives less than or equal to 9 homework problems as well. Let's look at part C. Part C wants to know the probability greater than or equal to 10. So in this case here, we're going in the other direction. Now, if you look at, we've already calculated less than or equal to 9. So greater than or equal to 10 would just be whatever's left over. And so these probabilities are, this is a true probability distribution. So they are going to add to 1. So in this case here, we can just do 1 minus what we calculated and subtract that from 1, you get about 0.2497. And the probability the class receives 10 or more homework problems would be about 24.97%. So that calculated work doesn't really need to be shown because we already did it, but you would take this number here and do 1 minus that to get 10 or more. Here's what the distribution is going to look like. So we don't have these theoretically go on forever because you can guess it on the 500th try, although it's very, very unlikely. So what's going to happen is the probability is going to be less and less each time as you increase your number of trials. So these are always going to be right skewed. Um, if the class played the game many, many times, how many homework problems would they receive on average? Well, if you think about it, we have a 1 in 7 probability. So the likelihood that we get it correct um, is going to be most common on the seventh try. So when we do this type of problem, these are always going to be skewed to the right. We expect there to be about 7 problems because there are 7 days in the week. And what do you think the standard deviation is? It's a little bit harder to tell, but you can utilize the fact that this is a right skewed to probably make some inference as to that standard deviation being maybe larger than you think it would be. So you see that skewness is really going to increase that standard deviation. We don't really have a way to use our calculator's stat menu to do that because these theoretically go on forever. So we have a formula, thank goodness. Um, and so we're actually provided these in our formula sheet. We have the probability distribution. So the probability is really just going to be the complement to the one less than how many times you want it to get it right at. The mean is always just going to be 1 over p. So if it's a 1/7 probability, then the mean is going to be 7. And the standard deviation has a specific formula, and you don't have to memorize that because that'll be provided on your formula sheet. The shape will always be skewed to the right, and we use PDF for an exact value and CDF for less than or equal to. So just remember these things here. C stands for cumulative. Now, with geometric, it's helpful if you think about bits, not bins. So T for the trials until you get your success. So that's kind of how I think of that. Everything else is the same as binomial, or binary, independent, and the same probability. And so on your formula sheet, it's going to be right here, right under a binomial, right under the discrete random variable, you'll have your formula for geometric. Your mean is just going to be 1 minus your probability, and your standard deviation is going to be the square root 1 minus p over p. So let's calculate how to get the mean and standard deviation. So I'm going to go back to my other one here, even though I didn't do it. I can show you what's going on with that. So the standard deviation, you might want to guess what that is. But if I go to my calculator and actually put in my probability is 1/7. So if I do the square root of 1 minus 1/7, and then I take that number and I divide by parentheses 1 over 7th, that'll actually give me my standard deviation for the Lucky Day game. So it'll have a pretty large standard deviation, about 6.48. Let's look at example 2. Suppose you roll a pair of fair 6-sided dice until you get doubles. Let t equal the number of rolls it takes. Note that the probability of getting doubles on any roll is 6 out of 36. So we're given the probability. And in this case here, that probability is going to be the same because they're rolling dice. So probability is going to be 1 out of 6. Now, the word until means that it's going to be geometric. So we have the same probability. It's going to be independent because we're rolling dice. It's binary. You either get doubles or you don't. So we're asked to show that it's a geometric random variable. We'll say it's binary, yes or no. We got independent. The rolls don't affect each other. The trials stop until you get your doubles, and the probability is always going to be the same, 1 out of 6. Now let's find the probability that t is equal to 3. So this is an exact number. So we would use, if we were to use our calculator, it'd be geometric PDF. But with these ones, I don't generally use the second vars because it's pretty easy to do without that. So equals is just going to be, hey, I want it to be doubles on the third try. So it's going to be not doubles, and then it's going to be doubles. So not's going to be, since doubles is 1 out of 6, not's going to be 5 out of 6 times 5 out of 6. And then doubles is just going to be 1 out of 6. So literally, you're just going to do 5, 6 times 5, 6 times 1, 6, and you'll be done with it. So that really is just the probability of getting doubles on the third attempt. So it looks like this. 5, 6 to the second power times 1/6, which gives you about 0.1157. I suppose if you wanted to use geometric, it would PDF, it wouldn't hurt you, but you have to make sure you write your inputs. So second vars, geometric PDF, P would be 1 divided by 6, and our X value would be 3. And there's your 11.57%. Part C, in the game of Monopoly, a player can get out of jail free by rolling doubles within 3 turns. Find the probability that this happens. So within 3 means 3 or less. So we want to know what's the probability of T being less than or equal to 3. So in this case here, we want to do 3, 2, and 1. Remember, we stop until we get a success. So there's no zeros because we are going to do at least one attempt. If we get it right on the first attempt, it's just going to be 1 out of 6. So the setup of that's going to look like this. Um, Let me kind of walk you through both ways to do it. So you could do the hand method. You could do 1/6 for the first try, and you could add that to the 5, 6 times 1/6, getting it doubles on the second, or what we just calculated, 5, 6 times 5, 6 times 1/6. And you add them all together, which isn't hard to do, but I would still recommend maybe doing geometric CDF on this one. Just make sure you write your inputs less than or equal to when you do that. And let's verify that we get the right answer. So geometric CDF is going to be second vars. I go up because it's at the very bottom. And then I do 1/6 and let my X value be 3. And that's 0.42, which is the same as doing 1 out of 6 plus 1. So let me do 5 out of 6. So 5 out of 6 times 5 out of 6 times 1 out of 6. I know this is a long way to do it, but that's okay. Oops, I forgot the second one. So 5 out of 6 times 1 out of 6. So I'm actually got it out of order there, but that should give me the same thing, which it does. And finally, calculate the mean and standard deviation of t, interpret these values. We actually have formulas for that. If you've identified it as a geometric, you would go into your formula sheet. You would look at the mean and standard deviation formula and plug them in. So let's do that. So our probability is 1/6. So our mean is going to be 1 divided by 1/6. And our standard deviation is going to be the square root. You got to be careful with this one. 1 minus 1/6 divided by 1/6. I would recommend using parentheses when you plug it into your calculator. And let's do that. So in our calculator, it's going to look like this. 1 divided by 1/6. So 1 divided by parentheses 1 divided by 6. And that'll be 6. You're just flipping the fraction. And then the standard deviation, I'm going to do the square root 1 minus 1/6. Close it up. Then I'm going to go outside and do divided by parentheses 1 divided by 6. You can use your fraction menu in your calculator if you'd like. And so the mean is, for many, many, many rolls, you would expect to get doubles on the 6th roll. And then the standard deviation would be, if for many, many rolls, the typical number of times it would take you to get doubles would vary 5.47 from the mean. So I put those into one description to make things a little bit easier for our interpretation. So I say, if we were to roll pairs of dice many, many times, the number of times it would take to get doubles would vary by about 5.477 times from the average of 6 times. All right, let's do a little check your understanding. On the check your understanding, there's a mix of binomial and geometric. So the first part, I think, is binomial, and the second part's geometric. So let's go through this. Suppose you have a very large bag of marbles. 40% of them are blue. Suppose you reach into the bag and pull out 6. Let X equal the number of marbles you get out of 6 selected. Assume independence since we're sampling less than 10% of the bag. So even though we're not putting them back in, we have a very large bag and we're told, you know what, 10% or less is fine. So we can still go through and do a binomial. We know it's binomial because we're pulling out exactly 6 marbles. So we want to know the probability that exactly 4 of them are blue. I'm going to do a binomial. Since it's an exact amount, I'm going to do a binomial PDF. So remember the formula, the setup is going to be you do 6 and you want to know choose 4. So that's going to be like NCR and NCR there. It's a combination. And then we multiply it by how many of them are blue. So the probability of getting blue is going to be 40%. So 0.4 to the fourth power. And then the probability of not getting blue is going to be 1 minus 0.4. And there's going to be 2 left over. So that's the formula says 6 minus 4, but we know that's going to be really 2. So if we clean that up, 6 choose 4. That off the top of my head, I don't know that number, but we'll calculate that. Times 0.4 to the fourth times 0.6 to the second. So 4 of them being blue and 2 of them being not blue. Now, in your calculator, it's going to look like this. So math, probability, NCR, you do 6, choose 4. This is a binomial because it's a set amount, so it's going to be actually 15. And it's going to be 15 times 0.4 to the fourth power times 0.6 squared. And that should give you about 13.82. So here's the typed out for you. We can also use binomial PDF since it's a specific amount. So in your calculator, binomial PDF would be second vars, go down to binom PDF. I write binomial, not binom. 6 trials, probability is going to be 0.4, and we want exactly 4 of them to be blue. And so there's your 13.82% as well. So either way is fine. If you're going to do it this way, make sure you write out all of your inputs, not just the number, comma number. All right, part B. What's the probability at least half of them are blue? At least half would be 3 or more. So I want to know the probability that X is greater than or equal to 3. So that's going to be a binomial again, but I would do a binomial CDF in this case. But remember that that's going to be the same as, since CDF goes at or below, the probability that X is less than or equal to 2. So let me set that up for you guys. On your calculator, it's going to look like this. I'm not going to even bother with the formula because we're doing so many at once. So we do second vars, go down to binomial, and we do CDF, not PDF. Our number of trials is still going to be 6. Our probability is going to be 0.4 again, but X value is going to be 2. And I forgot one thing on my write-up here. It's actually 1 minus that because remember, we're subtracting it from 1. So your final answer will be 1 minus that answer. The probability that means of getting at least half of them, so 3, 4, 5, or 6 of them being blue, is going to be about 45.56%. Here's what you'd write. I identify it as a binomial, so you have to write it as a binomial. It's the probability that X is greater than or equal to 3. So you're going to write all this information here, but as far as your work goes, you say binomial CDF, list your inputs, number of trials, the probability, Make sure you do less than or equal to 2. Don't just do x equals. Get that number, then subtract it from 1 and circle your final answer to get your credit. Lastly, what are the mean and standard deviation of x? And we have a formula for binomial. Remember, binomial is just the number of trials times the probability, and the standard deviation is the square root of that number times 1 minus the probability. So we can use that to get our mean and standard deviation. We'll go into our calculator and do that real quick. So the number of trials is 6. So 6 times the probability of success, which is 40%. We would expect to get about 2.4 blues. The standard deviation, square root, and it's the same number, 6 times 0.4, but then we multiply that by 1 minus that, which is 0.6. And there's your standard deviation, in this case 1.2. We weren't asked to interpret it, so I don't have to worry about that right now. Describe the shape of X. Use technology to graph. No, in this case here, it's kind of not really to your benefit to use your calculator to graph this histogram, but I'm going to show you something on Staplet real quick. So if you go to staplet.com, Stapplet, go to binomial distributions. We can do our set number, so 6, and then our probability is 0.4. We can plot that. You can see that histogram gives you a slight right skewed shape. And if you change that probability to something like 0.2, you can see it's even more right skewed. So the closer that your probability is to 50%, the more symmetric it's going to be. If you do a really high probability, it'll be left skewed. And of course, the number of trials, if I do like 100 trials, that really would impact the skewness as well. Because in this case here, even though it's a high probability, the number of trials is so high that it actually makes your distribution pretty close to symmetric. Because you rarely, even though it's possible, you don't really have much of a probability of getting any of these. So what we would say in this case here is it would be slightly skewed to the right. Looks like it's peaked at 2. And that's what binomial, not all binomials are skewed right, but in this case, it's a little bit skewed to the right. And then letter E. What is the probability that it takes 6 attempts to finally draw a blue marble? But this case here, we have a different scenario. Suppose now that you decide to pull out one marble at a time until you get a blue marble. So in this case here, the word until means that it's going to be geometric, not binomial. So let y equal the number of attempts it takes to get that blue marble. Again, assume independence since we're going to be sampling a small percentage of the bag. So we want to know the probability that it takes 6 attempts to finally draw a blue marble. Well, let's do our geometric here. We'll go through and do the calculation on our calculator as well. So this is going to be 5 not blues, and then that last one's going to be blue, so 0.4. So that's going to look like this. You can do 0.6. Remember, the probability of not getting blue is 60%, and then times 0.4. We only do one success because we stop on the last success. So there's your 3.11%. You can also do geometric PDF, not CDF, because it's an exact amount. So our probability is 0.4. Our X value is going to be 6. And there's your 3.11% as well. Find the mean, interpret this value. We'll use our formula. So the probability, the mean for geometric probability is 1 divided by the probability. So 1 divided by 0.4, that's going to be, let's see, 4 out of 10 is 2/5. 5 divided by 2, it should be 2.5. We'll double check that. So 1 divided by 0.4, which means that we would expect to get a blue upon the of many, many draws. We would expect the average amount of times to get the blue would be 2.5. Sorry, kind of a word garbage jumble there. So 1 divided by 0.4 for many, many marble draws in this bag, it would take on average 2.5 draws to get a blue marble. Find the standard deviation of y, interpret this value. So again, we're going to use that formula sheet. When we have our standard deviation formula over here, so let's plug that into our calculator. Just do square root, see 1 minus 0.4. Make sure you go out of the square root or press enter, and then divide that by 0.4. And that gets you 1.93. You can use your fraction menu too if you want. You just do like alpha y equals n over d. And you can do the square root on top, 1 minus 0.4. And then you can go down to the bottom and do 0.4. Whatever works for you guys. So 1.936 would be your standard deviation. Over many, many trials, the number of times it takes to get a blue varies from the mean by 1.93. So the write-up would be for many, many marble draws in this bag, the number of attempts it would take until you get a blue would vary by about 1.936 attempts from the mean, which was 2.5. Would you be surprised if it took someone 6 attempts to finally draw a blue marble? So in this question is really asking you guys, like, what's the probability of getting 6 or more? Okay. When it says, would you be surprised? You want to go in the more extreme direction. So if someone took 6 attempts, really saying, what's the probability of, what's our variable here? Y. Y is greater than or equal to 6. So this is, again, geometrics go on forever. So you really have to do 1 minus the probability that Y is less than or equal to 5 on this one. Since we have 1, 2, 3, 4, 5, we're going to use a CDF on this one. So we want to do geometric CDF. CDF, cumulative. And our probability is going to still be 0.4. Our Y value, it's going to say X in the calculator, but we say X, Y is less than or equal to 5. And then we subtract that from 1. So let's put that into the calculator, see what we get. So let's see. We're going to do second bars, geometric CDF, right way at the bottom. P is 0.4. Our X value would be 5. And we get 0.9224. So we take that away from 1. And we get about 7.8%. And so in this case here, because that's not an unusually small percent, remember our threshold's typically about 5%. I wouldn't say that's a surprising result. That can be gotten pretty, I mean, not regularly, but it can be gotten not as a rare occurrence. So what I would say on this problem is no. The geometric CDF will get you a 0.707776 since the probability of it taking 6 more attempts until blue is not unusually small. And again, we don't want it to be we don't want it to be less than 5% for it to be unusually small. We shouldn't be surprised in this scenario. So that's really it. This is a pretty quick lesson, hopefully for y'all, and it's just kind of builds on binomial. So it's basically covers what binomial doesn't. So just remember in this case your bits, and remember the t really is like until you get the same probability. So it's not a set number like binomial. That's really the only difference on this case here. Hopefully this was helpful. Thanks for watching.